Thank you. Yes, you can hear me. So it occurred to me to check that the Tate's thesis was defended in 1950, probably in May 1950, and I just checked that the NSF was founded in May 1950, and I think I can have some confidence that the Tate's thesis, people will still be talking about Tate's thesis 75 years from now, if there are people. But the NSF, I'm less confident about the NSF. Maybe even 5 years from now. So when I arrived at Harvard in the middle of the 1970s, as a graduate student, I already was familiar with the framework of algebraic number theory that Tate had constructed. Thinking back about it, it's amazing that he had done so much in such a short time, but it was already well understood and well established, and I wanted to work in algebraic number theory. And Tate was advising his students to work in the Langlands program, and I wasn't interested in that. So at the time, didn't quite see the point. But you know, things have changed. I won't be talking about very much that's new, only maybe if there's some time at the end. I will be explaining mainly how Tate's thesis, through the years, especially around the time I was a student, and then beyond that, it informed the Langlands program in more ways than you might suspect. So let me start very simply. So sometimes we write the Riemann zeta function as a sum, and sometimes we write it as a product. And we can also write the Dirichlet L functions as a product or a sum for real part of S greater than 1. And as you see, this chi is a primitive character. And so the L function, Dirichlet L function for character is the zeta function when the character is trivial. They come to life, so to speak, when multiplied by an Archimedean factor. And so we write the function lambda. Then we can do the same thing for the Dirichlet L functions. And L infinity takes has a different form depending on whether the character, the value at -1 is plus or minus 1. And if you believe Wikipedia, the factor in front of the zeta function was not well understood at the time of Riemann. What does it mean for? It's quite transparent what it means, but what was it? Whether it was understood or not is a philosophical point. But in any case, with Tate's thesis, it became understood in a certain sense because it was shown that this so-called gamma factor, this is a quotation from Wikipedia, is in fact the local L factor corresponding to the Archimedean place. All right. Well, the purpose of Tate's thesis was to reprove the functional equations of Hecke in a different way using Fourier analysis. The lambda Riemann's, that was not Riemann's notation, but it's the notation for the product with the Archimedean factor. It has this functional equation, the meromorphic extension with simple poles. And if you take a primitive Dirichlet character, then there is also a functional equation, but it's a bit more complicated. First, the character changes to its inverse, and then it gets multiplied by this factor, this epsilon factor, which has no better name than epsilon factor, which in this case is the quotient of a Gauss sum attached to the character by a power by either 1 or I times the square root of the conductor. right? So that's all familiar, and it was well known when Tate started writing his thesis. A little bit of notation, nothing surprising. OK is the ring of algebraic integers of a field, number field K. The completions, I say they're denoted either K sub P or K sub V, but in fact, I think I only used the V. And then KV can also denote the completion of a real embedding or a pair of complex conjugate embeddings. So we're going to use a uniform notation for the places of K and then the integer rings when the place is a non-Archimedean. And then sometimes there is a uniformizer, and Q, or Q sub V, is the order of the residue field. All right, that's the notation. Now, I was advised that not necessarily everybody, there may be nobody in this room who does not know what an Adele ring is, but just in case, you take this product and you take the limit, direct limit, co-limit over the n's, where n divides n prime. So this is a locally compact topological field, which therefore admits abstract harmonic analysis. The Adele group is the multiplicative group, and we can define more general Adele groups for finite extensions of Q, or of function fields, which will also be part of the story. And here S is a finite set of prime ideals, and the colimit is taken with respect to inclusions. The Hecke character, well, there's more than one way to define it. We say it's a continuous homomorphism from the Adele group to C star, which is trivial on the embedded multiplicative group of the field itself. And once you define one, you can restrict it to the different factors in the product. So that chi sub V denote the restriction to the multiplicative group of the completion at the place V. So for any element of the group, it's chi of the Adele A is the product of the local factors. This is the finite product. And then we can define the Hecke L function, L series. The L, there are people who do not make the distinction between the L and the lambda, but I will do that. So L is the product of the local factors, 1 minus the character at the uniformizer times Q to the minus S inverse for almost all finite V, 1 for the others, and then with appropriate gamma factors from the two options that I indicated previously. All right, so then you have that. Tate and Iwasawa independently and at approximately the same time obtained the analytic continuation and functional equations of the completed L functions with the lambda, with the gamma factors, by writing them as integrals over the Adele group and using the Fourier inversion theorem to relate the two sides. Right? And I have not actually seen, well, I think Iwasawa wrote it in Japanese, and then there are some notes that circulate. I've never seen a complete account of Iwasawa's version. But Tate did something else. Tate introduced the new method of local functional equations, which I wrote many years later, and then I realized many years later was about 20 years later, and 20 years later was 55 years ago. So whether this is many years later or not is a matter of where you're looking from. But at the time, it seemed to be many years later. It provided the basis for the general theory of automorphic L functions. So here's the starting point of Tate's thesis, and I will try to go through it in order to highlight the similarities with what followed. So you have to define the Schwartz space of functions on the Adeles. And for the finite, this is the restricted tensor product, which I won't explain. But it's restricted in the same way that the Adels are restricted. So for the non-Archimedean factors, this consists in the locally constant, compactly supported functions on the field, and they are the Schwartz functions, which are in the Archimedean places, which are functions, C infinity functions that are rapidly decreasing with all their derivatives. And in fact, so I don't even know whether Iwasawa was working in this language or not. This is Schwartz. The relevant property of these spaces is that they are preserved by a Fourier transform properties. So now, in most of this theory, you need to choose an additive character, that is to say, a character of the Adels modulo principal Adels, non-trivial character. And Tate verified that the Fourier transform on the Adel group with respect to this choice of character, any choice of character, you just have to remember that there is one, defines an automorphism of the Schwartz space. So it's denoted, phi goes to phi hat. And now, here is the Adelic integral. You take the Hecke character of K and a Schwartz function, and now you integrate, you introduce a complex variable S, and for a sufficiently large real part of S, this converges, absolutely, and you integrate the character times the power of the Adel norm, the S power of the Adel norm, times this Schwartz function. And it's an easy exercise to show that this looks like the kind of integral that Hecke wrote, or sums of such integrals. The Schwartz function turns the integral into something over the integers, essentially. And then there's the global functional equation, which is, you replace S by 1 minus S, and chi by chi inverse, and phi by the Fourier transform. So, and it's obviously symmetric, so if you do it twice, you get back to where you were. And the proof is just as in Hecke's proof, it's by Poisson summation. All right. Sorry? Oh, phi of A, you're right, yes. Yes, thank you. I thought I actually did find some typos yesterday, but not all of them. Yes, yes, so this is, where? Oh, sorry. Do I have to, where's the pointer? Yes, that is a typo. Okay, thanks. All right, so far we have not proved the functional equation of the L function. We've proved the functional equation of this zeta integral, which depends on an extraneous variable, which is this Schwartz function phi. And in fact, instead of thinking of it as an integral with a value as a function, you can think of it as a distribution on the Schwartz space, which is a useful way to look at it. So then we write the global functional equation, just z of S chi is the Fourier transform of a z of 1 minus S chi inverse, where the only thing that's missing is the dependence on this additive character. The Fourier transform depends on the choice of the additive character, but the global integral does not. And that's because we're working with a Hecke character. But if I could have written this down. This is an integral over the Adel group, not over the Adel class group. And although the Adel group is not, the Adel group is not literally a product, a direct product, the integral factors is a product over the local places. So the integral on this slide is a local factor of the integral in the previous slide, and the global integral is the product, again, for sufficiently large real part of S, of the local integrals, and the distribution is the product of the local distributions. And the local distribution does depend on the local factor of the additive character. All right. And here's the local functional equation. For each place V, there is a local Euler factor. You know what it is because you've already seen it on a previous slide, but you don't have to know. The method shows that there is a local Euler factor plus an entire function, which is a new object, epsilon of S, depending on the local data, the local multiplicative and local additive characters, such that the following equation of entire non-vanishing distributions, so now you have a distribution-valued function on C, and it's entire non-vanishing, and you have this identity. Identity is one of the words you're not supposed to use in your NSF proposal, by the way. So I'm not sure how many other words I've already proscribed words that you've already seen. So this is now the local functional equation, and this is the principal innovation of Tate's thesis. Of course, he also innovated the proof of the global functional equation, but he was not the only one. Iwasawa did that as well. And so now this entire non-vanishing function, epsilon, and what it says is that if the zeta integral can have a pole, but it will only have a pole if locally, that is, the distribution, you can remove that pole by dividing by this Euler factor. And of course, Tate also calculated the Euler factors, and since he knew the answer, he was glad to see that it came out right. If chi is an unramified character, then it is the factor that I wrote down previously. Otherwise, it's 1, which I also wrote down. And the epsilon factor is the Gauss sum, again, normalized by the discriminant. And again, if V is Archimedean, then L is an exponential of some power of pi multiplied by a gamma function, and epsilon is the power of I, which there aren't that many. Okay, but now, if you have the global functional equation and all the local functional equations, you just have to divide one by the other, and then the functional equation of the L function pops out. So you let lambda be the product over all places of the local L factors, and epsilon, the product of the local epsilon factors, and you show that that product, unlike the individual terms, is independent of the global choice of additive character. And then you divide one by the product of the others, and you get Hecke's functional equation. All right, so you not only get Hecke's functional equation, but now it's well understood. It was not well understood before, and now it is well understood. And strangely enough, it seems to me, Tate produced this monument, and then he never returned to it, or never in his publications. Although, in a sense, he did, and we'll see that in a moment. Well, of course, Tate was also busy with class field theory, so had an excuse. So if chi is a finite order, it corresponds by class field theory to a character of the Galois group, unramified outside a finite set. And we can define the L function of the character to be that's R chi, that's another misprint. Let me point out the misprint. That should be an R chi, a rho chi. So you take the product over for the unramified places of the image of Frobenius, and that gives you the same thing, and it is the same thing as that's what class field theory tells you. It's the same as the LS chi that was written as an adelic integral. And so LS rho chi also satisfies the functional equation. Why does it satisfy it? Because it is equal to the L function that whose functional equation we've already proved. So now we have something, again, that was already known, that the L functions of one-dimensional representations of the Galois group correspond to have functional equations, analytic meromorphic continuation functional equation. Now, you get more than that. You don't get all of the Hecke characters, but if chi sub v is an algebraic character for Archimedean v, then often, or maybe usually, if there's some technical condition, you get a compatible family of L-adic Galois representations with the property that, roughly speaking, because there's some normalization involved, the image of the Frobenius at unramified places is an algebraic number independent of L. So here I'm referring to Hecke characters of type A0 in We's terminology. So we have such characters. Chi is a Hecke character. Chi sub v is assumed to be algebraic, and then these other conditions, and we get this compatible family of L-adic Galois representations. And we've seen quite a few of those in the past 2 days. And so we can define, so we started with a Hecke character. We noted that there are these Galois representations, but we already have the L function, so we give a new name to the L function that we already have, and then we say that such a compatible family of Galois representations satisfies the functional equation. All right. But now let's look at non-abelian L functions, starting with the Artin L functions. So suppose you have a homomorphism from the Galois group to the complex matrices, so with the continuous homomorphism, hence with finite image, and you assume it's unramified outside a finite set. Now for each decomposition group, local Galois group, we let rho sub v be its restriction. And then we define the L function to be the product of the local factors, where now, if it's unramified, we take the determinant. We've already seen this term, the determinant of the identity minus the image of Frobenius, multiplied by q to the minus s inverse. And then if it's ramified, then we have to take the image of Frobenius on the fixed points of the fixed space of inertia. Well, again, as practically everybody here knows, together with Hecke's functional equation in class field theory and Brouwer's theorem on characters, induced characters, we know that LS rho has a meromorphic continuation and satisfies a global functional equation. And the functional equation, this epsilon, is obtained by multiplying, taking a alternating product of various epsilon factors of induced representations. Right? A meromorphic continuation, of course, Artin conjecture is that it, in fact, is entire if rho is irreducible. But I'm not going to talk about that. Joe Buehler is going to talk about some instances of that. But instead, I'm going to stress a conjecture that Tate made at some point. I believe he made this conjecture. In any case, he assigned it to Dwork, and Dwork almost approved it. So for any representation complex representation of the decomposition group and choosing an additive character of the field. So I didn't say it, but this is a non-Archimedean local field. There is an entire function of S, rho, and psi with the following property. Suppose rho is the restriction, doesn't define it uniquely. Suppose rho is the restriction of global representation, rho, in principle of Artin representation, and psi is a global additive character. Then the product of the epsilons is the constant in the global functional equation of the previous page of the Artin-L function. All right, that's a conjecture. Now, what was he thinking? I did not consult these collected works. I did not think of consulting his collected works. So I don't know what he was thinking at the time, because he certainly was not yet thinking about the Langlands program. But this was, why should there be, clearly there's his proof of the functional equation of Hecke-L functions exhibited the global constant in that functional equation as a product of local constants. And so the question is essentially why, when you apply Brouwer's theorem to write the global functional equation, why is this independent of the way you wrote it? That's essentially what he's asking. So you have a local epsilon factor now. So it was proved in Dwork's thesis up to sign. Then many years later, so to speak, it was proved by Langlands by a long calculation, as in his paper on I think it's called the functional equation of Artin-L functions, or it was. And it was a long calculation, 200 pages, using explicit relations among products of Gauss sums. Deligne soon gave a much simpler global proof by introducing the important notion of stability, which means if you twist by a highly ramified character, any local epsilon factor becomes essentially trivial. And then he characterized the local constants in abstract terms, essentially in terms of their behavior under induced representations. He also emphasized that the local constants gave the right functional equations for certain non-abelian L-adic representations that are not of finite order, not Artin representations, L-adic representations, as such as the ones that had been constructed by Eichler and Shimura for modular forms of weight 2, and then by Deligne for modular forms of any weight. So Deligne's proof was published in a volume of the Proceedings of the 1972 Antwerp Conference. He also presented his reading of the Jacques Langlands book and simplified some of the arguments, and his framework for the local Langlands correspondence for GL2. Introduced what's now called the Vey-Deligne group. And as in Jacques Langlands, a local functional equation in the style of Tate is central. And the method of stability that he introduced in order to prove this factorization, the existence of a local constants, is one of the standard methods of people who work on representations of L functions, automorphic L functions, and functional equations, in order to characterize local Langlands correspondences for groups other than GL2. Here's some acknowledgement of the role of Tate's thesis. The right way to establish the functional equation for the Dirichlet series associated with the automorphic forms, in this case in GL2, is probably that of Tate. And Gaudemont-Jacquet, a little bit later, it is natural to ask if it is possible to extend Tate's technique to GL2. Okay, I want to mention another idea that was relevant at the time. Vey reinterpreted the local theory of Tate's thesis in terms of distributions. Think of this distribution Again, so it's a distribution on short spaces. I didn't put the phi into the integral. And observes that it's equivariant with respect to the action of GL1. In the sense, if you define an action of GL1 on distributions dually to the action on functions, as one usually does, then the relation is that R here, then it has this relation. Note y is written on the right because it's going to be written on the right when it's non-abelian as well. And then you see that this notation is probably impossible to read. What it says is that it is in the space of distributions equivariant or with respect to this character that transform under the action of GL1 with respect to this character. This notation means that when you act on the distribution this way, you get the distribution multiplied by this. Okay. Well, if omega is not the trivial character, then the space of equivariant or distributions with character omega is of dimension 1. And this is because there's a short exact sequence of distributions of the distribution spaces, dual spaces. So with the dual space, the distribution space in the middle, and on one here there is the delta distribution at the point, because F is the union of F star and 0, so it's two orbits. The transitivity of the action on itself implies the multiplicity 1 claim. This one here, omega 0 acts, but no other omega appears here. So this property is an interpretation of the local functional equation because the Fourier transform with respect to psi is equivariant with respect to this character. And then the epsilon factor turns out to be the constant of proportionality between the distribution written in two different ways. Okay, only the trivial character is supported on the delta distribution. That explains the pole. And there are the space of distributions supported at 0 in R is infinite dimensional, and this is why the gamma factor shows up, which has infinitely many poles. This y is again, this is whether this is well understood or not is a matter of taste. Well, now I'm going to consider some group theory. So let F be a non-Archimedean local field, G an algebraic group over F. I think why am I doing this? Yes, okay. All right, so I've introduced I'm a little bit behind schedule, I see. I've introduced the principal series representations. If you take a Borel subgroup of G, if there is a Borel subgroup, and you say the representation is unramified, if there is a character, this is incorrect, chi from the torus to C star, but this character has to be unramified. That means it has to be trivial on the maximal compact subgroup. I forgot that. Such that pi is isomorphic to the normalized induction from the Borel subgroup to the full group of chi. And the general fact, if G is a group over a global field, then an automorphic representation is isomorphic to the restricted tensor product where almost all the factors are unramified. And now the analysis of zeta integrals in terms of equivariant distributions, following, as in Wei's reinterpretation of Tate's thesis, has been central in the development of the theory of automorphic L functions. So the key notion for Jacques Langlands was the Whittaker model, which I think I will skip and go directly to the Godemont-Jacquet version. So now we can take any GLN, or multiplicative group of any simple algebra. And in complete analogy with Tate's functional equation, you define the Schwartz space. You can define the Schwartz space completely analogously with respect to any vector group over K, and you take a function in the Schwartz space over the matrix group. The character is replaced now by a cusp form in this automorphic representation, and we define an endomorphism of pi as follows. So now it's an endomorphism. It's an endomorphism valued distribution. All right. So now we have the integral. It looks exactly the same as the integral, except that for some reason I put the phi on the left instead of on the right, with the determinant rather than with just the absolute value. And the global functional equation is proved, again, once you deal with the convergence questions, is proved by Poisson summation. The integral factors as a product of local integrals, and each local integral has its own local functional equation, which looks very similar to the functional equation of Tate. And furthermore, if the local factor is a supercuspidal representation, then the local functional equation follows directly. It's hinted at, although not said explicitly in the Gaudemont-Jacquet book. It follows directly from multiplicity 1 for equivariant distributions. Now, thinking of GL, if you now stratify the matrix space by the different ranks of matrices, then you have the invertible matrices are the open orbit, and the supercuspidal representations only integrate against the open orbit, and so they don't have any poles. That's why there are no poles, and that's why you have the epsilon factor comes out, again, in exactly the same way as Vey explained. Yes, that's where I should be. All right, let me just mention one more thing that you can do with this local factorization. You know, you think that Tate introduced all these general Schwartz functions, and then you have the symmetry property, but what do you do with the other zeta integrals? Well, if you've ever worked with p-adic L functions, you know that you need to put other data into the integral. And this first example may have been the work of Kajdan and Maser in the 1970s, which were later published in 2000 with Schmidt. And actually, the main calculation in my paper with Eischen, Lee, and Skinner for p-adic L functions for unitary groups makes direct use of the Gaudemont-Jacquet local functional equation. It's long enough without that, but even after that, but with that, it makes it much shorter. All right, let me say very quickly, there are also L functions for tensor products, Rankin-Selberg L functions. If this is why I introduced the principal series. So suppose you have cuspidal automorphic representations now of GLN and GLM over some field K, and you consider the L function, which is the product of local factors for almost all V. Remember, as I said, you have unramified factors. That means that you can replace the pi by an n tuple of complex numbers, and you can replace the sigma by an m tuple of complex numbers, and you write down the local Euler factor in this form. It's just multiplying the different possible products of alphas and betas. Now, the Rankin-Selberg method of Jacquet, Piatetsky, Shapiro, and Chaleika is an adaptation of Tate's method to obtain local and global functional equations for these L functions. I haven't told you what the local factors are at the ramified primes. And it took quite some time for them to work out all the details, but it's and the Tate's method, you have to look at it carefully to realize that that's just what they're doing, but that's in fact what they're doing. Now there's another way to get the same L function to the Langlands-Shahidi method using, but again, you get the global functional equation from the theory of Eisenstein series, you use uniqueness of Whittaker models to obtain the factorization, and then you use local intertwining operators, that's in the representation theory of GLN, to obtain the local functional equation. So ultimately, you end up with the same thing, you have a global functional equation, and the factor, the epsilon factor, is a product of local factors. I'm going to rewrite this. So here, the local functional equation looks like this. So I have, this is a global functional equation. In fact, I said it was a local functional equation. This is in fact a global functional equation. The sign depends on m and n, and there is a slight modification to go from the r. There you have to translate one of the elements. It's rather elaborate to write down all the details, but ultimately it does come down to a Fourier transform. And now I introduce the gamma factor, because the people who work in this area prefer to package all of the epsilon and the L factors together as one, and then you have the epsilon factor multiplied by the L factor from one side. This is local, divided by the L factor from the other side. And now I'm going to skip this. Yes. Oh. So I wanted to say how Tate returned to his thesis. He returned to it indirectly. As I said, Tate contributed to the Langlands program, made a very significant contribution by encouraging several of his students to work in the area. And so these were the students who were at Harvard when I was, who overlapped with me. And they all wrote theses that became part of the program. And 3 of them wrote chapters for the proceedings of the 1977 Corvallis conference that for over 40 years remained the official reference for the whole area. And Tate contributed the chapter that remains the standard reference for the Galois theoretic aspect of the Langlands program, in particular emphasizing the epsilon factors. And Dick Rose was also a student, but he was not working in this area at the time. He joined eventually. All right, well, let me say something briefly about the local Langlands correspondence for GLN. So, some notation, we let phi of GLN over F be the set of local Langlands parameters, that is to say, Frobenius semi-simple homomorphisms from the Vedolin group to GLN of an algebraically closed characteristic zero field. And let pi GLN over F be the set of irreducible admissible representations of GLN F over C. So a local Langlands correspondence is a bijection between the two sides with certain properties. The key property that was identified by NER, as I'll explain, has to do with the local functional equation. So the local functional equation includes, as I indicated, the definition of local constants for, again, they depend on so if you have GLN cross GLM of this local field, you have representations pi v and sigma v, then you get a local constant. And then, now suppose we have 2 Vedolin representations of dimensions n and m respectively, and we define a gamma factor and just by imitating the definition for the automorphic gamma factor. Then the theorem is that there exists a unique set of correspondences satisfying the expected series of properties, and notably the gamma factors coincide. All right, so this was proved in 3 different ways, in my book with Taylor, by NER, and later by Scholze, and had already been proved for fields of positive characteristic, Lomont, Rappaport-Stuhler, and Laurent Laforgue, in these cases, all cases, by using the properties of the global Langlands correspondence. And the uniqueness statement in the correspondence was proved by NER, and who, as I said, emphasized the characterization by the local constants. No analogous characterization is known, or at least I know of no analogous characterization for the hypothetical local correspondence for groups other than GLN. And in fact, and the point I want to make is that in all proofs, in all the known proofs of the local correspondence, the result on epsilon factors was obtained directly by adapting Deline's, the article of Deline in which he constructed Tate's local constants. It's a global to local argument, in fact. The local information is obtained by applying the global functional equations and then the compatibility of local and global functional equations. Now, I want very briefly to talk about the Selberg trace formula, the Arthur-Selberg trace formula. That don't have much time. So there's a non-abelian analog of the subject of Tate's thesis. It's the spectral theory of automorphic forms on reductive groups. So suppose G, to simplify a connected semi-simple group, could be reductive, but then notation is more complicated, over, it should be a number or function field. And consider the space of discrete automorphic forms. It decomposes as a countable direct sum of representations of the Adele group. Pi runs over all irreducible admissible representations of this global Adele group, which has to be understood in the appropriate way if it's a number field. And it's a sum, but for all but countably many pi, the multiplicity is 0. So the spectral theory consists in determining the integers m of pi, and specifically why when m of pi is greater than 0. This aspect of the theory is still, there are still people who study this, and this was what was emphasized in the 50s and 60s, how to find ways to find the multiplicity. Langland's first paper in this area was on the use of the trace formula to study the multiplicities, but then later he discovered functoriality, and that's been the emphasis ever since. Well, how do you calculate the multiplicities, as already Langland's understood in his first paper? When the representation is defined to have a character, and it's a distribution on smooth, compactly supported functions, locally constant functions if it's a function field. And if pi is irreducible admissible, the trace is defined and often written chi sub pi, and therefore one also proves that the trace on the discrete spectrum is defined. That's not so easy. And Arthur went to a lot of trouble to obtain this. And then once you have that, it is equal to the sum of the characters with their multiplicities. So that's one way to do the spectral theory by calculating the trace. Now, this is only useful if you have another way of calculating the trace. And so you use the analog of the Poisson summation formula, which a non-abelian analog, which is the Arthur-Selberg trace formula, about which I fortunately don't have very much time, so you won't have to see it. But I just want to show you that this is what you want to know, and then this is what you can calculate, and these are orbital integrals. If you were working with finite groups, then this would be completely familiar. But now it's an identity of distributions. And you can ignore the formula. Well, it is essentially an integral over this. So what's important is that this is an adelic integral, and this is so adelic meaning it factors over the different places, and here you have something that is a volume that is global. It's a global in nature. So you have a global term plus a term that is, they call it local because it factors over the places. And then I'm going to be quoting the stable trace formula, which replaces the sum over conjugacy classes by a sum over stable conjugacy classes, but it has not been written down yet, but K is a function field. In fact, even the invariant trace formula is not yet complete, although there's ongoing work and there's been considerable progress in recent years. So in the last few minutes, we were going to travel 5 years into the future so that we can make free use of the stable trace formula for function fields. The full stable trace formula was developed over several decades in an interplay between the global theory and the harmonic analysis on local groups, and is extremely complicated to describe. But here is a quotation from Noah's paper in which he proves the fundamental lemma. It says, you get your information about the local orbital integrals by a global argument, and then you turn it around and you get the complete stabilization of the global term. So you can't separate the two. But there are many other examples of this type of argument in the theory of the trace formula. So this is, in the last 5 minutes, I say something new. So let G be split semi-simple over a local field of positive characteristic. Let phi G over F, again, be the set of Langland's parameters. And let pi of G over F be the set of irreducible admissible representations of the group over any field, algebraically closed field of characteristic 0. So this is joint work with Bazar-Plessis and Jack Thorne. So suppose you have an irreducible parameter. Now, and suppose, and these are presumably temporary restrictions. Suppose P is prime to the order of the Weil group, and at present, with reference to some unwritten papers of other people, there may be an additional, stronger condition on P, but sufficiently large P. And suppose there is a stable twisted trace formula over function fields in a form adequate for stable cyclic base change. So Lebesgue wrote a book in which he formalized stable cyclic base change using much less than what's known now. Then phi is the image of a supercuspidal representation under the local parameterization of Genestier-Laforgue or Falk-Schulze. Moreover, pi is generic. It has a Whittaker model. In general, there's supposed to be more than one supercuspidal representation. Oh, well, in general, there can be more than one, but there should be only one generic. It's conjecture that there always is at least a generic representation. All right. Actually, one gets a result that's somewhat weaker for p-adic fields. So using the results of Lee Huerta on the compatibility of a Falk-Schulze correspondence with the Deligne-Kazdan theory of close local fields, the result for equal characteristic has the following corollary. So suppose you have a p-adic field. Again, you have an irreducible parameter. So I didn't say what a parameter is. A parameter in this case means a homomorphism to the dual group. Did I write the dual group? Yeah, okay, I did. I didn't say what it was. That is the dual group. This thing is the Langland's dual group. Just showed up. So you have a parameter. Suppose tau is trivial on the inertia subgroup of level n into the upper numbering. Then there is a positive integer, d, greater than or equal to 2n plus 1, which can be determined more or less effectively, but such that if the absolute ramification index of f is at least d, I think I had my the quantifiers in the wrong order, so it seems to depend on tau. It really only depends on n. D depends on n only. Then there is a supercuspidal representation whose Falk-Schulze parameter is the given tau, and moreover pi is generic. So I actually have enough time to explain the structure of the argument. So first, you choose a global function field with a given place, such that the completion of the function field is your given field f. Next, you globalize phi to a homomorphism with the Zariski dense image. And this uses, among other things, this uses the techniques of deformation theory of representations, and in particular the Carré-Venton-Berger method to get a lift to characteristic 0. Then using the results of my paper with Buckle, Carré, and Thorne, we show to show that rho is potentially automorphic. That is to say, it is automorphic. It becomes the image of the global Laforgue parameterization over some Galois extension, L. All right, and then there's an elementary reduction to assume that pi is everywhere unramified. You can make some solvable base change to get everywhere unramified. Therefore, because it's unramified, in particular, it's locally generic everywhere. It's unramified. I should explain. It's unramified. It's also of weight 0, pure of weight